Hello, good morning everybody. Welcome to my video. So today we're going to talk about graphs. So what are graphs? Generally we denote the graph by GVE, where V stands for the whole set of all vertices and E stands for the set of all edges. You may ask, what are vertices and what are edges? So now I have a graph to give you a more obvious explanation. So in this graph we have A, B, C, D, E, F, G, H, I as vertices or nodes, if you want to call it that more obvious way. And the line between each two of the nodes or two of the vertices are called edges. So now after you understand edges and vertices, we can go into some other terminologies, which will be the degree and order. So what is degree? Degree means the number of edges in the graph. So you can count, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 edges, so which means the graph has a degree of 10. And we have 9 nodes total, so we have an order of total of 9. In fact, degree can also be used to denote the number of edges connect to a node. So we can see the degree of A is 2 because we have 2 edges from A to B and E. After we know the fundamentals of vertices, edges, degrees, and order, we can think about, do we have one graph here or 2 graphs here? In fact, graphs don't have to be connected. So I want to introduce another term, which is connected component. So you can see there is a way to travel from A to F or A to C, but you cannot travel from A to G or H or I because there is no possible edges to do so. So under this circumstance, we can say there is a path from A to F because if we use all the edges in this part, then you can actually travel from A to F. But there's no path from A to G, H, or I. In this case, we call the part on the left as a connected component and the part on the right another connected component. And we want to make sure there is no path from one connected component to another connected component, because otherwise you just break the rule, break the definition. Then we know some basic terminologies, but I also want to know, how do we traverse the graph, which means how do we order the nodes in the graph. So I want to introduce 2 different ways you can traverse the graph. First, I will erase those nodes because I will use the area underneath to do some explanation. Well, we can start with the first way, which is called depth first search. First, I will assume you already know some fundamental knowledge of data structures, or otherwise I recommend you to watch some more basic, more easier videos about like stacks, queues, because we're going to use them later in the video. So depth first search rely on a stack. I will introduce the stack. You stack up from the bottom to the top, and you pop out the topmost element first. So let's say if you want to use breadth first search to search the left connected component. Let's say if you want to start with A. So first we add A to the stack. And then we look at what are some other connected nodes from A which are not visited yet. In this case, we can choose either B or E. But to make this algorithm simpler, I will choose B. So we push B to the stack. Oh, actually, I need to add the list, add the ordering underneath. So it's A, B. So we have B in the stack now. So next we look at what are nodes connected with B which are not visited yet. Well, A is already visited, so we have D or E left. So for our benefit, I will choose D. So D is in the stack. Then we look at what are connected with D. We have C or F, and here I will choose C. So we have C in the stack. And we found out we reached the end. So what shall we do next? Well, we pop the C out of the stack. So C is out, we go back to C. C is out, we go back to D. We look at what if we have any possible connected vertex which are not visited yet. And we found out we can go to F. So we will push F to the stack. And add F here. And we found out F has one more connected vertex which can be visited, which is E. So we push E to the stack. And then we start popping out. We found out E has no more connected edges which are connected nodes which are unvisited. So we push out, pop out E, go back to F, and F is the same situation. We push F, pop F out, go back to D, and we pop D out, go back to B, and we pop B out, go back to A. And we found out we have all possible vertices visited. So A, B, D, C, F, E will be the result we get from depth first search. Next, I'm going to introduce a similar but different solution to traverse the graph, which is called breadth first search. Different from depth first search, breadth first search will rely on a queue instead. So we construct the queue up here. So just as the previous one, we start with A. So A is in the list. But instead, we directly move to B. We look at what are the edges, what are the nodes connected with A. So we found out B and E are both connected with A. So we will enqueue both B and E into the queue first. B and E into the queue. And then we dequeue A. A is here. And then we look at, then B will be the next element we care about. And we look at what are some vertices which are connected to B but not in the unvisited yet. And we found out we have D in the graph. So we will add D to the queue, and now we can dequeue B. And then we look at E next, and we look at what are some connected vertices of E, and we only have F left, so we enqueue F. And now we can dequeue E. And then we see D is the next in the queue. So we go to D, and we found out we have C, which is connected to D and unvisited. So we will enqueue C. And we can now dequeue D. And after that, we found out there's nothing else left. We look at F. F has no more unvisited connected vertices. So we just dequeue F and add F to the list. And we do the same thing for C. So A, B, E, D, F, C will be the result we get from breadth first search.